Okay, this is our last lecture for Unit 8 for Algebra 2. This one, 8.10, is essentially going to talk about variation models. Which we will get into what those are. There are three types of variation models. Variation is essentially a special relationship between variables. There are certain relationships between variables that are so common and that we see so often that we distinctly label them. So the first one that we will talk about is direct variation. Now, direct variation model is something like y is equal to k times x. Where y is what we call directly proportional to x. The second one is what we call joint variation models. And this one would be something like y is equal to k times x times another variable z, where y varies as both x and z jointly vary. That's why we call it joint variation. And the third variation model that we will talk about is inverse variation. Whoops. Inverse variation is y is equal to essentially k over x. So this one we'd say where y is inversely proportional to x. It's important to note here that in all three of these variation models, y, x, and z are variables. K is what we call the constant of variation. But it is in fact a constant. So for the direct variation, what you're seeing is that y is equal to some constant times x. So when we say that it's directly proportional, or it's direct variation, if x were to increase, you would see that y would increase proportionally. If x decreases, y decreases proportionally. In joint variation, y will vary as both x and z vary, right? Because if you change x, y will change. If you change z, y will change. If you change them both, then y will also change. Inverse variation, that's because we've put x on the bottom, so it is now the inverse function. So this one is saying y is inversely proportional, so if x were to increase, y would decrease in this case. So the first thing that I'll have you do for variation models is just be able to determine what type of variation model are you looking at and what is the k value for that variation model. So determining model. So for example, if I gave you y is equal to 2x and I asked you whether or what type of variation model this was and what was the constant of variation, you should be able to tell me that this is direct variation with a k equals 2, because y is only dependent on x, and the constant in this equation is 2. If I said y is equal to 5x times z, this would be joint variation with k equal to 5. So those are some more obvious ones. you might need to make it a little bit of algebra to be able to figure out what type of variation it is. So for example, if I gave you 3y is equal to x, you need to manipulate this so that y is always what's being solved. So to get y on its own, you need to divide both sides by 3. You get y is equal to 1/3 x. So this is direct variation with k equal to 1/3. So it's very, very important that you're always solving for y for these. If I said, for example, x times y is equal to 36, you would need to divide by x to solve for y. So 36 over x. And you would then see that this is an inverse variation model with k equal to 36. I might not necessarily give you obvious variables like x, y, and z. You might have to use your intuition to figure out what I'm asking about. So for example, if I said 2a is equal to bh, well, this looks a lot like the rearranged equation for the area of a triangle. So if I divide by 2, you get that area is equal to 1/2 base times height. Well, then you can see that the area of a triangle is actually it's a joint variation model between b and h. So we would say that this is a joint variation model with the k equal to 1/2. So the area of a triangle is dependent on both the base and the height, and that makes sense. The next thing that I might have you do is write your own model based on words. So writing variation models. So for something like this, I might tell you if y is directly proportional to x and y equals 28 when x equals 7, find x when y equals 52. So the first thing that you'll want to do is write your variation model. The key word in this one is the word directly, so we know that this is directly proportional. So we can say that y and x, y is equal to k times x. So that is our direct proportion or direct variation model. So when y is equal to 28, when y is equal to 28, we have that x is equal to 7, so k times 7. If we divide both sides by 7, we get that k equals 4. So now we know that our model is y is equal to 4x. So now it's saying find x when y is equal to 52. So we get 52 is equal to 4 times x. And if we divide by 4, then we get that x is equal to 13. Now if I said that if r is directly proportional to the square of s and r is equal to 72 when s equals 12, find r when s equals 8. Okay, So here we say r is directly proportional to the square of s. Interesting. So if I said, okay, r is equal to the square of s, k times the square root of s, then we say r is equal to 72 when s is equal to 12. So if we square both sides to get rid of that square root, we could have 70, oops, let me turn my calculator on, 72 squared is equal to 5,184 is equal to k squared times 12. So I'll divide by 12. And I get 432 is equal to k squared, which means that k is equal to plus or minus the square root of 432, which is not a perfect square, and that is okay. So find r when s is equal to 8. Okay, so we know that r is equal to plus or minus the square root of 432 times the square root of 8. This is just plugging into my equation that I found in the beginning over here. Okay, so 432, we get that r is equal to plus or minus the square root of 3,456. Which simplifies, you can plug this one in your calculator. This will be plus or minus the square root of 58 point, looks like 79 about. That one was a little less nice to us. Let's do one more. If, for example, we say that the dollar amount, D, that Megan earns directly varies with the number of hours that she works, which makes sense. The more hours that you work, the more you should hopefully earn. So dollars is directly proportional to hours, is how I'm going to say that. So this is dollars. This is hours she works. So if in her last paycheck she earned $148.50, and she worked 18 hours, so this is equal to k times 18 hours. Figure out what the variation model is. Well, okay, this is pretty simple. So we would figure out, if we divide both sides by k, we get that k is equal to $8.25. So our variation model is dollars is equal to 8.25 times the number of hours that she works. So then if I asked you how many hours she worked if on her next paycheck she earned $90.75, you would say, okay, 90.75 is equal to 8.25 times h. If we divide both sides by 8.25, you would find that she ended up working 90.75 divided by 8.25. She worked 11 hours to earn that much. Okay, let's do some examples of different variation models. So if I say that if y varies jointly with x and z, and y equals 48 when x equals 8 and z equals 15. Find y when x equals 14 and z equals 20. So now the key for this one, unlike the other ones, is that the word is jointly. So our joint variation model says that y is equal to k times x times z. And this problem says, well, when y is equal to 48, then we know x is equal to 8 and z is equal to 15. So we can solve for k by dividing 48 by 8 times 15. So 48 divided by 8 divided by 15, this gives us a 0.4. So now we can say, okay, our joint variation model is actually y equals 0.4 x times z. So if we're trying to figure out y when x equals 14 and z equals 20, we can just plug that in. We get that y is equal to 112. Okay. If I said, if P varies jointly, again, keyword here will be jointly, as Q and the cube of R vary, and P equals 270 when Q equals 6 and R equals 3, find P when Q equals 3 and R equals 5. Okay, well, we're going to do our joint variation model again. So we get y is equal to k xz, which in this case it's actually P is equal to k and then Q and R. That's our basic one. According to this problem, P will vary jointly as Q and then the cube of R vary. So now we can, using this one, plug in the numbers we know. So P is equal to 270 when Q equals 6 and R equals 3. So we get that 270 equals K times 3 cubed is 27 times 6 is 162. So K equals 1 2/3. So now find P when Q equals 3 and R equals 5. So if we know that P is equal to 1 2/3 times our new Q of 3 and our new R of 5, we can plug this in and say, okay, that P is going to be equal to 1 2/3 times 3 times 5 cubed, which is equal to 625. Okay, another example. If I said, for Peter's savings account, the interest varies jointly with the principal, which is the initial amount, and amount of time in years, if Peter opened the account three years ago with $1,200 and has earned $144 so far in interest. It's pretty good. How much interest will he have earned in 8 years after opening the account? Okay, so this is a joint variation. So we get that maybe the dollars that he has is equal to K times the principal amount times the amount of time. Let's actually set this as I for interest. So interest is equal to K times the principal amount times time. So if we know that he's earned $144 and he put in $1,200 originally, and it earned that amount of interest in 3 years, we can solve for K by dividing 144 by 1,200 times 3. We get that K is 0.04. So now, if we're trying to figure out how much interest he earns, in 8 years, we can say, okay, that's 0.04 times the principal times the new time. So we get that 0.04 times 1,200 times now 8 years. So I get that after this amount of time, he will have earned $384 in interest. Let's do a few inverse variation model examples. So for example, if y is inversely related to x and y is equal to 7.5 when x equals 8, find x when y equals 5. Okay, so we have y is inversely proportional, so that's a k over x. When y is 7.5, x is 8. So if I multiply both sides by 8, I get that k is equal to 60. And I can now say, okay, my model is y is equal to 60 over x. So now find x when y equals 5. So I say 5 is equal to 60 over x. If I divide both sides by 60, I get that 5 over 60 equals 1 over x. So I'm going to have to then do the inverse. So I can say 60 over 5 is equal to x over 1, or just x, and that is equal to 12. Okay, let's do a little harder of example. If m is inversely proportional to the square root of n, and m equals 27 when n equals 16, find m when n equals 64. Okay, well, m is inversely proportional, so that will be a k over n. But it's inversely proportional to the square root of n, so let's put that in a square root. And then it says that m is equal to 27 when n is equal to 16. So we say, okay, 27 is equal to k over 4. If I multiply by 4, then I get that k is equal to 108. So now if I plug that in, I get that my model is m is equal to 108 over the square root of n. So now find m when n equals 64. M equals 108 over the square root of 64. So that's 108 over 8. And that will be 108 divided by 8, 13 and a half. Let me double check that. Yes. Great. Let's do another example for this one. The time it takes me to drive to Moab varies inversely with my speed. That makes sense, right? The faster I'm going, the shorter amount of time it will take me. If it takes me 8 hours at an average speed of 50 miles per hour, how long would it take me if I went 60 miles per hour on average? Okay, so time is inversely proportional to speed. So if it takes me 8 hours, if I'm going 50 miles per hour, then that means that k is equal to 8 times 50, which is 400. So that means my model is time equals 400 over speed. So how long would it take me if I went 60 miles an hour? Well, I'll say, okay, 400 over 60 miles per hour. So I'm going to divide 400 by 60, and I see that it'll only take me 6 2/3 hours. And that makes sense. The faster I go, the sooner I should get there. I just want to do a few more examples now on combined variation. So this is actually our last type of model, and this is combined variation model. This is when you have a model that contains both direct and inverse variation models. So for example, if I said y varies directly as x and inversely as z. So you say, okay, y is equal to, and I know that it's varying directly with x, so that would look like this. But then it's also varying inversely with z, which would be a k over z. You don't have to double up on the constants because they're just some unknown constant. So you can just mush these together and say that y is equal to some constant times x over z. So now you can see that as x would increase, y would increase, but it's inverse to z because z is on the bottom. If I said that p varies inversely with q squared and directly with r cubed, you can say, okay, p varies inversely, so that'll be a k over q and then squared. And then also, it is varying directly, so a k times r cubed. Again, you don't have to double up the constants because it's just some unknown constant. So you can say that p varies directly with r cubed, but inversely with q squared. And you would be done. Last example here. So if we said that a varies directly as b and inversely as c, if a equals 16 when b equals 12 and c equals 6, find a when b equals 28 and c equals 4. Okay, so a varies directly with b, so that'd be k times b. And then a varies inversely with c, so that'd be k over c. So my mushed up model is a is equal to a k times b over c. If I plug in the values that I know that a equals 16 when b equals 12 and c equals 6. So I can reduce this and say that that is 2 times k. If I divide by 2 on each side, I see that k is equal to 8. So I can say, okay, my actual model is a is equal to 8b over c. So now if I plug in my new values, I get 8 times 28 over 4. So 8 times 28 divided by 4 will give me 56. And that's it for this unit. Please go ahead and start working on this homework and email me with any questions.